Thanks a lot. Thanks a lot for having me here. I've had great fun attending this workshop or conference. So I'm a physicist, not a mathematician, as the title makes it clear. And the goal of my talk is to provide a new explicit formula for the Kawazumi-Zhang invariant, which is a real-analytic function on the moduli space of compact genus-two Riemann surfaces, which has an important role in Arakelov geometry, arithmetic geometry, and it's a close cousin of the Folting's invariant. I don't know too much about the whole mathematical framework, but I will present some background to set up the scene. And so the formula was actually guessed by studying two-loop scattering amplitudes in string theory, but the formula stands on its own feet, and I will say very little about string theory. It's actually completely explicit, and it's suitable for numerical evaluation. And I think it comes short of being a theorem because there is some technical vanishing theorem that needs to be proven, and I'm hoping to get feedback from you to help me on this, possibly. But I think it is pretty trustworthy. And one interesting point about it is that although it's a real analytic function, I will show that it derives from a holomorphic function on the Siegel upper half plane. However, this function has mock modular properties. So it's kind of an interesting example of a mock modular form. So you can find this on the archive and on this. Good. So I'm going to start with some background. So this Kawazumi-Zhang invariant was introduced, I think, independently by those two authors in 2008. And so it's a function phi of sigma. So everywhere sigma will be a compact genus-two Riemann surface. And there are many ways of defining it, but one interesting way that makes connection to Arakelov geometry is the following. So you consider the spectrum of the Arakelov Laplacian. It has eigenvalues, I'm going to define it in a second. It has eigenvalues lambda L, and you make a sum of all strictly positive eigenvalues of the following of 2 over lambda times a certain norm. So the norm is defined as a sum over pairs of holomorphic differential. Actually, first of all, let me start with arbitrary genus, because this object is defined for arbitrary genus, although the formula I will propose will be specific for genus-two. And so here's the formula. You're supposed to integrate over sigma the eigenfunctions phi L times omega m wedge omega bar n modulo square. So what is the notation here? So omega m equals 1 to h is a orthonormal basis of holomorphic differential, holomorphic one forms. So phi L are the eigenmodes of the Arakelov Laplacian. Delta sigma phi L, this is not the same phi as the curly phi over there, is lambda L times phi L. What is delta sigma? Well, delta sigma is defined by the following property, that if you take any function f, you consider del bar of f, and it's proportional to the canonical 1,1 form. So, and the proportionality factor is the Laplacian, Arakelov Laplacian on it. So I'm sort of defining things backward, but this canonical 1,1 form u sigma is just the sum of this of the modular square of this holomorphic one forms. So up to some numerical factor I over 2h. This is the sum of omega m wedge omega m bar. M equals 1 to h. So it's the pullback of 1,1 form on the Jacobian of sigma, which will play a role in the later formulations. So of course there is a 0 eigenvalue, which you need to remove, and then you take all the other ones. And so this in particular makes it clear that this is a real value function which is real and positive. And here, of course, I'm ordering the eigenvalues from lambda 0 equals 0, lambda 1, lambda 2, etc. And it only depends on the complex structure of this Riemann surface. So in fact, it pulls back to a function on the Siegel hyperhalf plane that, well, in genus-two, it pulls back to a function on the Siegel hyperhalf plane. Otherwise, it's just a function on the moduli space of compact genus-two Riemann surfaces of MH. Okay, that's one definition. It's not very suitable for if you want to compute a number out of it. So there are several variants which I will explain. So first of all, a relation to the Foltings invariant. So in fact, de Jong, based on earlier work, so in 2013, by Wentworth, showed a relation, a linear relation between this Kawazumi-Zhang invariant phi of sigma, at least a relation which is valid on hyperelliptic locus. Hyperelliptic locus. He showed that phi of sigma was actually equal to some number times the Foltings invariant of sigma, plus some other explicit number times the log of the discriminant, which is well defined if you have a hyperelliptic model, plus some other constant. All those numbers are well known, but I'm not writing them. Maybe I should put 3 dots on this equal sign and just remove the constants. So specifically for h equals to 2, this will be useful. For h equals to 2, of course, all genus-two Riemann surfaces are hyperelliptic, so there's no restriction. And in fact, we have phi of sigma is equal minus 5/2 of the Foltings invariant, minus 3 times the log of the norm of the discriminant, which in this case is just the Iguzakis form of weight 10. So this norm here involves an absolute square as well as the power of the determinant of the period matrix to make it modular invariant, plus a constant which I won't bother about. Okay, so this is definition number 2. Well, it's a relation to a quantity which was defined earlier, back to Foltings. Third relation, just for curiosity, because it won't be so useful, is this Foltings invariant is related to the log of the regularized Laplacian. So minus 6 log of det prime of delta sigma divided by the area of sigma measured in the Arakelov metric plus some constant. So this determinant, of course, has a 0 eigenvalue, which you need to remove it and define the determinant by some zeta function regularization technique. So anyway, the take-home message is that this Foltings invariant is related to a log of Laplacian on Riemann surface. Now we come to more computationally useful formulas, which are specific. This was for any genus still. Now we're back to genus-two again. There is a formula due to Bost in 87, which expresses the Foltings invariant in terms of an integral over the Jacobian of this genus-two Riemann surface. Well, first there is a contribution again from the discriminant, but the non-trivial part of it is an integral over J of sigma, which is an abelian variety of complex dimension 2, of, again, this canonical, well, the square of the canonical 1,1 form on the Jacobian, which is now a 2,2 form, weighted by the log of the norm of the genus-two theta function. Okay? And, well, in the early days, this was how these numbers were actually computed numerically. Very good. And this formula is actually useful to establish certain limit asymptotic behaviors, which will be important in my talk. But let me first state, oops, sorry. Good. Let me state the most useful definition for all purposes, which actually is where we make contact with string theory. And this was, I think, by Kawazumi in 2008. This is now an way, again, now this is, I should say, for any h. I'm sorry to I'm trying to be as general as possible, so sometimes I can give the general result, sometimes not. So in that case, it's an integral over the product of two copies of this Riemann surface of a certain by two form, nu of z and w, times the Arakelov-Green function z of w, where the Arakelov-Green function, so it's a function of 2 points on each copy, such that if you take dd bar with respect to the first variable, well, it's the inverse of the Laplacian, so it has a delta function source at w, and then some constant such that it's orthogonal to, the right-hand side is orthogonal to constant. Or if you like, g of z and w will just be, again, a spectral sum over all L of these eigenvalues, eigenmodes phi L of z, phi L of w, divided by lambda L. Whereas this two form, so by two form, well, is the, again, we're using the canonical 1,1 form for each variables, u of w, so this is pulled back to sigma. But then there is some, okay, this formula is actually not so important. Let me just write it for completeness. So if y is the period, if omega equals x plus iy is the period matrix, then you take the imaginary part, you take the inverse of it, y n q minus 1 omega m omega bar n of z omega p of w omega bar q of w. Okay. Well, actually, this formula is what comes out of string theory, although you may not care about it. But just a word about this. If you, so maybe I write this. If you write this here. So in type 2 string theory, compactified on a certain torus of dimension d, so it's a very supersymmetric situation. You look at a certain four-graviton scattering amplitude. At so-called order, well, 4 gravitons means 4 powers of the Riemann tensor in the low energy effective action and 6 derivatives acting on it. Whatever it is, the quantity of interest turns out to be, so this amplitude is a modular integral of this Kawazumi-Zhang invariant. So it's an integral over the fundamental domain of the genus-two, well, the degree 2 Siegel half plane for the full SP4 symplectic group of this phi. So phi, I can think of it as a function of sigma or just as a function of the period matrix in genus-two times a certain Siegel theta series. We call it Siegel-Narain theta series. For a lattice of, so there's some lattice lambda of signature d, so it's just a sum of hyperbolic lattices. So this is a function not only on the period matrix, but also of some, well, maybe I should, some variable, I don't know, rho, yeah, let's say rho which is lived in some Grassmannian, which parameterize the space of such self-dual lattices. So anyway, by this kind of modular integral, you produce a function on the space of lattices, which must be automorphic under the action of the orthogonal of the automorphisms of that lattice. So in particular, we're interested in computing such modular integrals of Kawazumi-Zhang invariant and some other modular form. And so this kind of information is not enough for us to make this computation. And at the end, if I have time, I'll present some applications of the new formula which go in this direction. OK. Now, I need a few more properties, however. So degeneration limits. So the way I'm going to produce the new formula is by proposing a function which satisfies the same degeneration limits as that one. So this is why I'm going to spend a bit of time on this. Yes? Oh, yes, sorry. This is the fundamental domain. Well, I guess this is H2 mod SP4. OK, so the kind of degeneration limits that we're interested in for functions on the Siegel upper half plane of degree 2 involve the limits towards two divisors. There is the separating degeneration. So this is the divisor where, so let me use parameterize omega, the period matrix, as rho, sigma, v, and v. So this is the divisor where v is equal to 0. And so the stabilizer of this divisor is a subgroup of SP4, namely just SL2 acting on a rho variable. Sorry, it's not the same rho as over there. I apologize for the notation. Cross SL2 acting on the sigma variable. All right. So what is known from actually, well, several of these definitions. OK, let me not. So this is essentially the work of Wentworth. Is that this phi has actually a logarithmic singularity as v goes to 0. So it goes like the log of 2 pi, of the modulus of 2 pi v, Dedekind square of rho, Dedekind square of sigma, plus some order v square log v behavior. So it's real-analytic on the moduli space of genus-two Riemann surfaces, but not on the Siegel upper half plane. It has this logarithmic singularity on the diagonal locus. There is another useful degeneration, the non-separating one. So this is where, I guess one way to define it, the divisor DNS is when sigma goes to I infinity. Not sure if my notation is very rigorous, but it conveys the idea. And so in this, it's much more tricky in this limit, actually. So if I studying this limit is equivalent to understanding the Fourier-Jacobi expansion of this modular form. And so it's useful to parameterize the period matrix in this way. So the rho variable, again, on the upper half plane of degree 1, introduce two real variables, u1, u2 for the off-diagonal part, and then redefine the imaginary part of omega, of this entry of omega, as t plus rho 2 u2 square, where, as usual, being a physicist, my notation is that rho is rho 1 plus I rho 2, real and imaginary part. So what is known in this limit is that this phi of omega actually grows linearly in this parameter t. So this is the same as t goes to infinity. And so at first order is just a linear behavior in t. But then there is some order 1 correction, which has to be, of course, a Jacobi form under so the Fourier Jacobi group, which is preserved, which is the stabilizer of this divisor. So it turns out to be actually the genus-one Kawazumi-Zhang invariant, but this is just the log of the Jacobi theta function as a function of rho u2 minus u1 divided by Dedekind. So it's maybe it's just, you call it theta, I think. It's just the usual Jacobi theta function. So is the one corresponding to odd spin structure, if you like. And then there is some order 1 over T behavior, which was not known in the math literature. Now, okay, I need to take another board. Finally, as far as limits goes, there's one further piece of information that we want to use. That is the so-called tropical limit. And if you like, it's near the maximal singularity, so which is the self-intersection of the non-separating degeneration. Okay? So this basically means that you scale all entries in the imaginary part of the period matrix to infinity. And it's useful to use actually yet another parameterization in this limit, because SP4 gets broken to GL2Z across some three-dimensional translation group. And so it's useful to make this symmetry manifest to define, to factor out the volume, the determinant of this period matrix times a quadratic form of determinant 1, which I can parameterize again by parameter tau in the Poincare graph plane. And there the limit here is somewhat more, takes some. So this is actually somewhat conjectural, I think, but it's a conjecture which is based on Auer, and that comes from string theory, but I think it can also be made precise purely on mathematical ground. And this says that as a function of this determinant, so this grows like the determinant to the 1/2, so this is pi over v times. So you would think it has to be a function which is automorphic on a GL2Z, and it is, but it's discontinuous. So it's kind of interesting object. That's why I spent 2 minutes on it. So it takes a little bit of notation to write it down. But so as a function, again, of tau, of the tau2, the imaginary part of tau, it has behavior of order tau2, 1 over tau2 and 1 over tau2 cube, T1 square over tau2 cube plus order v square. And the notation here is that T1 is in fact, is the absolute value of tau1 minus tau2 square. So if I drew a picture, I won't do it here, but so in this tau upper half plane, the fundamental domain of GLZ action is 1/2 of the usual fundamental domain, and this function has some some discontinuity in the first derivative over there. Okay, so this is actually a new result, but a conjecture. Now I want to get to the final piece of data, which will allow us to identify this function in more mundane terms. What am I doing in time? Okay. So the really new hint that gave us the clue is identification of a differential operator which annihilates this object. So here's a theorem, I would call it, which is based on my paper with Eric Docker, Green, Rodolfo Russo, 2014. And actually, this part of the paper is really due to Eric Docker, who is a master of Siegel modular forms, let's say, or Riemann surfaces. Anyway, the theorem says that if you act with a Laplacian on the upper half plane with a specific eigenvalue, well, you get almost zero. You get zero everywhere away from the separating locus. So this delta function support just reflects the singularity in log of v that we had over there, and everywhere else is just an eigenmode. And the proof actually so the proof uses the representation of phi as an integral over the product of two Riemann surfaces plus deformation theory of complex structures. So this is a very strong constraint on this invariant, and we can make a few consistency checks on this by looking at the various degeneration limits. So first of all, this tropical limit turns out to be exactly consistent with this equation. So remarks, tropical limit satisfies this differential equation. How about the non-separating degeneration? So near this non-separating divisor, well, the first two terms do not actually quite suffice to satisfy this equation. So we need extra order 1 over t term. So I'm going to write this I'll call phi 0. So let me just write this as pi over 6t plus phi 0 plus phi 1 over t plus, in general, order 1 over t squared. And so the way to repair this formula is to add a certain phi 1. And so using tropical limit, so this phi 1 as a function is a real-analytic Jacobi form of weight 0. So as a function of rho and v, or u1, u2, well, it must have some polynomial growth. So some number, 5 power 6, rho 2 square, u2 square, u2 minus 1 square, plus 1 over rho 2. And if you have ever played with Kronecker-Eisenstein series, you will immediately recognize this as the limiting behavior of the following Jacobi form, a real-analytic Jacobi form. Well, maybe not immediately, but after just a little bit of trial and error, here is what it is. So along with the differential equation, so differential equation plus this imply that we have a sum Kronecker-Eisenstein series, so the sum over mn different from 0, 0. So 1 minus cos 2 pi mu1 plus nu2 divided by m rho plus n to the fourth, rho 2 squared. So the claim is that this actually, so this choice, so choosing fits, of course, fits the bill with exponential at order, with exponential accuracy. What I mean by that is that by adding this term, in fact, this formula So I won't call it phi, but so this formula plus order e to the minus 1 over e to the minus t is actually a solution to this differential equation at this order. And so this is a very good guess for what could be the leading subleading behavior of this phi, even though we don't have this is not a proof at this point, it's just an indication. But if it is true, it also implies an additional correction to this tropical limit. And the additional correction turns out, from expanding this Eisenstein series, turns out to be of the expected order. So we go like order v squared times delta 3, plus again order e to the minus 1 over v, so up to exponential accuracy. So again, this part, well, this is a double conjecture at this point, but it will follow from the formula which I will propose. Are there any questions at this point?
What is the physical significance
of this? Yeah, so in fact, we guess this formula by analyzing the supersymmetric constraints on these amplitudes over there. It requires that so this automorphic function on the Grassmannian must be solve some Laplace equation, some Poisson equation with a certain source term. And if you track, you also know that the Siegel-Narain theta series satisfies such a Laplace equation. So if you trace it back, you lead to this equation for the integrand. Oh, y5, no, okay, I'll tell you in private. But that 5 is the same as this 5. But anyways. Okay, so this was basically the background part of the talk, even though I've mentioned a few new results along the way. Now let me get to the actual proposal. Okay, so let's call this, I call it a proposal, but I think, with little effort, it should become a theorem. So define phi twiddle of omega. So basically, the idea of the construction is a theta lift from a almost holomorphic Jacobi form of index 1 and degree minus 2 onto a real-analytic Siegel modular form of weight 0. So the formula should probably not be a surprise to most of you, but it's good to make it explicit. So it's I write it as in the following way. So it's a modular integral over the fundamental domain of the Poincare of a half plane of degree 1. So I like very explicit formulas. And so there is a lattice partition function of signature 3,2. We call that SP4 is SO 3,2 over the reals and so on. So, well, I want to write it as a modular integral over the full fundamental domain for the full modular group. So I need two pieces to achieve this. So I'll define H0 odd d H1. So, well, this d, first of all, is the mass raising operator at genus-1. What are those partition functions, those lattice theta series? So gamma 3, 2, whether it's even or odd. So again, it's a function of omega as well as on tau. And basically, it's a sum over 5 integers, m1, m2, n1, n2, all in z, as well an integer b, which can be in z even or can be in z odd, of q to the q to the 1, okay, some normalizations to p right square, q bar, p left square, q is e to the 2 pi I tau, Okay, so this is the usual thing. I think everyone probably has seen this, so I should not spend too much of time on this. More interesting is what are these H0 and H1. So H0 and H1 are the theta series coefficients, the coefficients of the theta series decomposition of the following Jacobi form, so weakly holomorphic, weak Jacobi form of weight -2, index 1. I guess there's only one probably, so theta 1 square, theta square over eta to the 6 as a function of the v and, well, tau, I guess, variable has two components. So there is, let me write it, yeah, so it's H0 of tau, theta 3 of 2z, 2v 2 tau, plus H1 tau, theta 2 of 2v 2 tau. Okay, that's it. I think the formula should be completely explicit and clear. Now I can state the proposal, which of course is what you expect. So let's see what do I need to. Yeah, okay, so if I just write one of them and you can guess the other one. So P right is M2 minus M1 rho plus sigma N1 plus rho sigma minus V square N2 minus BV, and you divide this by the square root of the determinant. Yeah. Okay. Good. So I think I don't need. Well, let me move this up. Good. Okay, so proposition, if you like, this phi twiddle of omega is, of course, is a real analytic Siegel modular function on H2 minus the divisor, so this separating divisor. It has same asymptotics as phi of omega near, well, ds, dns, non-separating, as well as this tropical limit, dns cube. And moreover, it satisfies same differential equation. Now that's, okay, that should be pretty obvious. Well, the differential equation is a consequence of the property satisfied by this lattice, narrowing lattice of signature 3,2. The delta function singularity on the right-hand side, again, originates from the behavior near the separating degeneration, which essentially comes from a null vector in this lattice. And well, the behavior here is a little more tricky, but it requires using the unfolding method of I guess, Borcherds and others, but it can be made very explicit. And in particular, not only satisfies this asymptotics as phi omega, but also this improved asymptotics, which I guessed earlier by using information from the Laplace equation as well as also tropical limit. So conjecture phi equals phi twiddle. Now, how much do I need to prove to make this, to turn this into a theorem? So the difference, phi minus phi twiddle, will be annihilated by this Laplacian. Phi minus phi twiddle is equal to 0, and phi minus phi twiddle is of order 1 over t in near the near separating degeneration, and order, well, it could be of order v squared log v near the separating node. So, well, it's clear that you cannot have any contamination from cos forms because the eigenvalue here is positive. You can also rule out Eisenstein series. The one thing which I haven't quite ruled out is Klingon-Eisenstein series, and I need some help to learn this. But anyway, I think this is on pretty safe ground, unless people feel differently. But anyways, this is the conjecture. And now, if there are no questions about the conjecture. Oh, L2, no, it's not L2 because the eigenvalue has the wrong sign.
Yeah, or maybe it's L1 plus epsilon.
Okay, so we can discuss it maybe. I don't know on top of my head, but if you think that allows to answer the question, I'd be happy to look at it more closely. Okay, so now I can turn to corollaries. I have a few minutes for this. So one corollary, of course, is that this improved asymptotics hold true. But you have more than this. This I keep for later. So I guess this is, well, corollaries. Well, first of all, there is a complete asymptotic expansion that you can obtain by using these unfolding methods. How does it look like? Well, near the separating divisor, the ns phi will be, this pi t over 6 plus phi 0 plus phi 1 over t plus an infinite sum of exponentially suppressed contributions which are computable. And those are, in fact, determined by the Fourier coefficients 4kl minus b squared times a certain sum of polylogarithms. I'll just write it. So there are the so-called Bloch-Wiener-Ramakrishnan dialogues, or polylogs, which appear naturally in this story, in this type of integrals, plus 1/2 4kl minus b squared times the d1 polylog. The sum here runs over k strictly bigger than 0. Well, first of all, x is my shorthand for e to the 2 pi I k sigma plus bv plus l rho. K runs positive, L positive, B in Z. And these polylogs have explicit form, so d1 of x is just the real part, basically, of log 1 minus x. The d2 of x is the real part of log li3 of x minus log mod x li2 of x. Anyway, so those are some pretty explicit formulas, which no, okay, the nomenclature, this is probably a bad notation, but the formula is correct as it is if you use the notation from Zagier in his paper on Ramakrishnan, etc. polygon. But yeah, it's degree 1. Yeah, it is a trilog. And I did not define what these C coefficients are, but maybe I should write it there. So F0 of 4 tau plus H1 of 4 tau is sum of Cn due to the n. By the way, I should have made a comment about this. So of course this is a close cousin of well, this is a variant of Kawai's formula for log of psi 10, right? Where instead of using this weight -2 guy, you would use the weight 0, which is the elliptic genus of K3. In that case, you actually need to regularize the integral. There's a constant term. Here there is no constant term, so this is all perfectly well defined. Okay, so this is and so everything is okay. I guess I really have to speed up now. Well, I'm pretty close to the end. So, what are other corollaries? Of course, there are similar formulas, similar near the non-separating, the tropical limit, or near the separating node. More interesting is the point I was anticipating at the beginning, which is a holomorphic function behind this object. So, okay, so this phi, if the conjecture holds true, is in fact the real part of the action of the mass-raising operator on the Siegel half-plane of degree 2 on a certain holomorphic function, which I call f, where and the weight here is -2, where f is purely holomorphic, while it has some polynomial part with some numerical coefficients, rho plus sigma minus 2v. Sorry. So it's a degree 3 polynomial plus a constant proportional to zeta 3, not surprisingly, plus a sum of trilogs, sum over KLB over the same C4KL minus B square Li3 of X. So in fact, this is true up to this is ambiguous up to quadratic polynomial in rho sigma v, which lie in the kernel of this mass operator, raising operator. But it is true, nevertheless. This is one particular choice. And so it implies, because this phi is a modular invariant and the raising operator also preserves modularity, it follows that this, this is actually called prepotential in the string theory literature, so supergravity. It follows that this object transforms like a mock modular form. So if I act with weight -2 with some SP4 element, I will get the same. This f up to some polynomial, which depends on gamma as well as on omega, which is degree 2. So, well, to be honest, I know this for sure when gamma is in the Fourier Jacobi group. So, preserving the cusp. So in SP, in SL2 rho, cross Z2 cross Z. But I think this, so at least, but I think this is more true more generally. That is, in this case, I can compute this polynomial. So I'm just about to stop. So this is one example, I think, of a more general construction. You could feed here not only some, you could change the depth of this object, include some d to the n, lower the weight here, and in this way you will get a family of Siegel modular forms which are related to holomorphic mock, which have some holomorphic mock behavior, so which may be of interest to some of you. I think I should stop here.